Yeah, so let me briefly recap what we've learned in our previous lectures. So we decided to study electrostatics in free space, and then we learned two important theorems, right? First is Coulomb's law, and the other is Gauss' law. Coulomb's law is very straightforward. It's just these equations like Q1, Q2 divided by R squared. And then by performing this integration, like for the point charge, line charge, surface charge, and volume charge, you can calculate the electric field due to a given charge distribution, right? So in these calculations, the only thing important is you know how to express these terms like dl or r as a function of given coordinate variables, right? And as I said earlier, in order to specify the source coordinates, source positions, I use primed coordinate. And in order to specify the point of interest, I use unprimed coordinate variables. And then we move to Gauss' law. So what Gauss' law says is that if you take the closed surface integral of a electric field flux, this is equal to the charge enclosed charge amount divided by epsilon naught. Okay, and then in our previous lecture, I gave you some examples of Gauss' law, and then these examples we learned how to apply symmetry argument, right? So this part is important. So I'll say a little bit more about this. So again, like E field can have three components: EX, EY, EZ, right? And then each of these components can be dependent on XYZ coordinate, XYZ position. So there are 9 possibilities, right? XYZ of E field component, and for each component can be dependent on XYZ coordinate variables. So there are 9 possibilities. And then by applying symmetry argument, we rule out most of the possibilities. Like for instance, in this case, we know that E should only have ER component, right? And then E theta and E phi component must be 0, right? By symmetry argument. And then by doing this, we remove these 2 possibilities, which actually correspond to 6 possibilities if you take into account this XYZ dependence. And then due to the symmetry again, R theta. And due to the symmetry, ER can only depend on R in this case and cannot depend on theta or phi, right? So we remove 2 more possibilities. So there are the only possibility left is E, which is ER as a function of R, AR. Extremely simple function. And then we apply Gauss' law, right? And then the next steps are just straightforward. Let's see, just the flux integration and the charge amount calculation. These are straightforward things. What's important is the process of removing these possibilities, ruling out these possibilities, right? And then we practice this thing for another 2 cases of infinite line charges and also infinite charged sheet. Okay. And then finally, we have one more exercise, which is a uniformly charged sphere. So in this case, as we discussed earlier, when you are in a bulk, like if you are in a bulk sphere, like when R is smaller than A, then the electric field is proportional to R, linearly proportional to R. And then this is kind of clear from the previous examples. You remember that if you have a point charge, E is proportional to 1 over R squared. If you have a line charge, E is proportional to 1 over R. If you have a surface, E is proportional to R to the 0, which is not proportional to R. I mean, there's no dependence. Now you have a sphere, and then you are inside the sphere, then E is proportional to R. Okay, if you look at the dimensionality, you know, it's just you having like you can see the order. And then if you are out of the sphere, then all of a sudden the problem becomes equivalent to a electric field due to a point charge, because the symmetry is exactly the same, right? The symmetry is the same. And if you think about the enclosed charge amount, it doesn't matter whether your charges are concentrated at the origin or you have a charge distribution with a sphere. And some of you may ask like something like this. Okay, then if that's the same, then why it's same as the charge at the center? Why not like charge at the off the center? Well, if this is the case, then this system and the original system have different symmetry, right? So these point charge and this charge sphere have different symmetry. So we cannot consider them equivalent in terms of Gauss theorem. But if the charge is located here, then the symmetry is preserved. Charge amount is also preserved. So the results are the same. And just going back to what I just said, let's assume that, let's just compare the situation where you have a charge, point charge at off center, like here, with the same charge amount of this sphere. And even in this case, because the enclosed charge amount by this Gaussian surface is exactly the same, so if you take the integration value must be Q divided by 4 pi epsilon naught, okay, for both cases. What's different is the electric field distribution, okay? So what I'm saying is that if you integrate electric field flux on the passing through the spherical surface, that value should be same as Q divided by 4 pi epsilon naught for both cases, right? But in this case, where you have charge at the off center, you don't know the electric field value at each position from this value, right? Because you don't have symmetry that you can apply. So you don't know like what component this electric field would have. So now if you draw your electric field intensity as a function of R, you see when R is smaller than A, it's linear like this. And then when R is larger than A, it becomes decreases as a function of 1 over R squared, like just same as the point charge. So this is the electric field distribution. Okay, so is there any question so far? By the way, your attendance and the participation status is posted on KLMS webpage. There's a link to that you can check your participation status and the attendance. So just check it if you're interested. So any question here? Nothing? Okay, so by the way, if you have any question, it doesn't matter, even though I'm talking about some other things, if you have a question about the previous subject, you can just type in the question in the chat box. Okay, and as I said, I want this course to be interactive as possible. So, don't hesitate to ask questions if you're not clear about anything. Okay, so this is about Gauss law. And then we will learn about the concept of electric potential and electrostatic energy. So potential and energy are the two things that we are going to learn from now on. So here, as I said earlier, like let's think about the work done in moving charge Q from point A to point B. Okay, then so let's say you have a charge here, then this charge will feel the force due to the electric field, right? Assuming that there is an electric field. And then you want to move this charge from this point to that point. And how much of work is required? In order to obtain that value, you have to take integration f dot dl from A to B, right? And then you have multiple choices in terms of path. So you can go from A to B through this path or that path or whatever path. I mean, there are like infinite number of paths. And then as we okay, so before we talk about anything mathematical, the potential difference between these two positions, so between A and B, is defined as this work divided by the charge amount Q. Okay, so that this concept can be applied to any charge amount. So it's basically normalized by charge amount. And then the potential difference between A and B can be defined as minus E dot dl from A to B, right? And then, as we learned earlier in the mathematics part, electrostatic field is conservative, right? Curl of E is 0. So VAB, this path integral, is path independent. And we learned why, right? Because curl of E is 0. By Stokes' theorem, the path integral for the closed loop is always 0, right? And then this closed loop is composed of A to B, say A to B through path 1, and then B to A along path 2, right? And then B to A, and then so if you rearrange this equation, this is like minus A to B along path 1 and B to A along path 2. And then this term is equal to A to B and then take a minus. So like integration from B to A is actually minus integration of A to B along path 2. So that's applied here, right? And then that means it doesn't matter like which path you choose in calculating this path integral. It should always be the same value, right? Because this equation holds for arbitrary choice of path 1 and path 2. So no matter which path you choose, your potential difference is defined uniquely, right? So this become a useful figure. Please ask any question if this is unclear. So what I said is just how to define potential difference between 2 points in space, and then also said this potential difference is unique value. It doesn't matter which path you choose in performing integration. No matter, like, regardless of the path, you will get the same answer. And then that originates from this property, curl of E is 0. Why E field is conservative? This is a nice question by from Kang Yung. By the way, thanks for asking the question. Why? This is a really good question, and I actually don't have a nice answer why the E field is conservative, because to me it sounds like why there is a gravitational force. It's kind of difficult to answer. It's like that's how nature is looks like. So if I give you a more detailed answer, actually curl of E is non-zero, and it's actually proportional to dB dt. Okay, and this is the full Maxwell's equation. And because we are dealing with electrostatic situation, nothing is moving, so dB dt is 0. And then in this electrostatic situation, and only in this situation, electric field is conservative. That's probably what I can tell. So you should keep in mind that in electrodynamic condition, where dB dt is non-zero, we cannot write electric field as a gradient of a scalar potential. Okay, this is possible. Like this, expressing electric field as a gradient of a scalar potential is possible only for electrostatic field. Okay, but this was a really good question. It's very, actually, it can be a very profound question. And when we define electric potential at point P, for instance, like point P, any point in space, we need a reference point, because as you learned, electric potential difference between two positions can be uniquely defined. But if somebody asks, okay, then what's the potential at this point? It's kind of a wrong statement, right? Because you don't specify any reference point. What you can tell is the potential difference, not the absolute potential, right? But there is convention. So when we say electric potential at point P, we assume there is a potential reference, and this potential reference is often set as infinity. Okay. So if somebody asks you, what's the electric potential P at some point, and without specifying anything, that means you can set the reference point to the infinity. Okay. And from this, you know that electric field can be written as a negative gradient of V. the scalar potential. Okay. Okay. And now, if you evaluate the electric, yeah. So now, if you look at the electric potential due to a charge, point charge, located at the origin. So let's say this is your charge Q. And then somebody asks you, what's the potential at this point, for instance. Then you can integrate your electric field. Electric potential due to a point charge Q at the origin. Yeah. So yeah, right. Here, and then you need to integrate your electric field from reference point, which is infinity, to the point of interest, P, right? And then your electric field can be obtained by Coulomb's law. So electric field is like Q divided by 4 pi epsilon 0 r squared along AR direction. And how to obtain this? How to perform this integration? There are multiple ways. As I said earlier, you can take integration from infinity to the point of P along arbitrary paths like this, probably path 1, or this can be a path 2. And then regardless which path you choose, your answer should be same, right? And if that's the case, which path you should choose in order to make your calculation easiest as possible? Which path should you choose? Can you type in the answer? Which path makes your life easier? Right, line like AR, right? So the easiest way is setting your reference to here, like along the R position, and make it infinitely far away, and then take integration along this line, right? Along AR straight line. Then this calculation becomes this, right? AR, the AR direction from infinity to R, right? Then the integration becomes very easy because your electric field is also AR direction. Your path is also AR direction. So this becomes just 1. And then your calculation becomes extremely easy. And you can get Q divided by 4 pi epsilon R as your answer. But as I said earlier, you can even try if you want. It doesn't matter which path you choose. So let's say this is P and this is Q. And you can set like arbitrary position. Let's say here as your it's okay if it's infinitely far away from the Q, and then you can choose like spiral position integration. You get the same answer. Okay, it just makes your calculation dirtier, but you get the same answer. So it's better if you just set it the integration along the straight line. Makes your life a lot easier, right? And then the electric potential due to a point charge at R prime. So now we assume that this point charge is located at R prime instead of origin. Then this equation can be written like this, right? R minus R prime. R prime is the source position, the position of the charge. And then we can expand this into multiple charges. Like if you have like Q1, Q2, Q3 located at R1, R2, R3, and Rn, you can just add them up, right? You can just apply a superposition principle and then just take a summation of this thing. Okay, so any question up to this point? So from now on, we are gonna learn why this is useful. But before then, I'll address Park Jun's question. Sorry, could you explain how the fact that V is the line integral of E leads to E? Oh, okay. So oh, I see. I thought that this is kind of trivial thing. So let's say, so V is some reference point to R, E dot dl. R is a position vector. Then okay, it can be not trivial for some of you. Okay, so for now, I'd rather leave it as your exercise because it's like right. So so as Park Jun said, okay, so I shouldn't say it's trivial. It's not trivial. It's not trivial, but you can just understand this as an extension of like the relation between 1D derivative and then 1D integration, right? If some quantity is an integration of something, then if you take the derivative, you can get the derivative. That applies to like multidimensional case too. So I don't want to spend time on detailed proof of it, but you can see the point, right? If it's 1D, then if V is an integration of E, then E is a differentiation of V. That's kind of related in this manner. Yeah. And Hong Won-gi asks why we can use superposition principle when we calculate the electric potential. Is there any effects of interaction between point charges? This is also a really good question, but it's like, yeah, it's the way it is. Like as we learned earlier, when we learned about like Coulomb's law, like we have 1 point charge, and then we calculate the electric field, and then we have multiple point charges, and then we obtain the electric field due to these multiple point charges. We apply a superposition principle, and then this is possible because the system is linear. And if you ask why the system is linear, it's hard to answer. It's like how it looks like. So it's kind of difficult to say, but yeah, but there's no how can I say, clear answer why the system is linear. But if I understand your question correctly, you may worry a little bit about like something like this. Like if you have 1 charge, and then if you have 2 charge, and if you have 3 charge, then you are worrying about the interaction between charges. And it is true that placing charges becomes more and more difficult as you add more charges, right? But this is about the interaction between the charges, right? And then what we are interested in is the electric field at this position, assuming that we were able to put the charges in this configuration. So regardless of how much energy is required in order to create this charge distribution, once we achieve this charge distribution, the electric field at this position can be obtained by just linearly adding the electric field due to each charge. And then I guess what you're worrying about is the interaction between the charges. And so I'm gonna address this later in this lecture, but in terms of energy, of course, you cannot just linearly add them. So like, the energy that is required to create this charge distribution increases quadratically, not linearly with the number of charges. But that's another topic, right? So for now, we are focusing about assuming that we have charge distribution. What's the electric field at P? And that's just linearly superposed. But if this, okay, good. And E. Jae-sung asks, can't electric potential be defined without reference? This is also a good question. And the answer is correct. Yes, electric potential, you can only define electric potential difference between two positions. And then if somebody asks you, what's the electric potential at just one point, then you always need reference. Like you need to specify reference. If somebody did not specify the reference, you can just assume it as an infinity. Okay, that's a kind of convention. But you can, yeah, you always need reference. Right. Just to give you an yeah, I'd rather not. Okay, so is there any other question? So electric potential itself is the integration of the electric field, right? And then electric field is about force, electric force. If you multiply Q to the electric field, you get force, physical quantity. And then because V is an integration of the electric field, it's always important to set the reference, right? It's just when you do the integration, there is a degree of freedom of the constant C, right? You can choose. So in order to define V in a proper manner, you always need reference point. Okay, so if there's no other question. By the way, thanks for everyone asking questions. It's very, these are all very nice questions. And some of them are profound. And if my answer was not satisfiable, then please ask a question again to further clear up. Okay, so let's look at the usage of electric potential. And as I said earlier, electric field has three components, right? E has EX, EY, EZ. But V has only one component because it's a scalar. Much easier to deal with. We don't need to worry about like complicated vector algebra. Now, the question is like this. You have an electric dipole. So you have a charge Q and charge minus Q separated by distance D. And here is the center, the origin. So this is a D divided by 2, D divided by 2. And then your point of interest P is very far away from the origin. Very, very far away. So you can say that R is much, much larger than D. Okay. Then what would be the electric field at the position P? So you can imagine how to evaluate this, right? So because you, due to the charge 1, you have an electric field like this. And due to the charge 2, you have an electric field like, say like that, right? Because it's opposite direction. And then you add them up, your electric field would be along this direction, right? You can guess the answer. But we need to know the general solution as a function of R. And of course, you can do this, you can do this calculation by dealing with the electric field. There's no problem, but it's just more complicated. So instead of dealing with Q, dealing with E, we can deal with V, okay? So V by the upper charge is Q divided by 4 pi epsilon naught R1, right? This is R1. And then this, the charge by the potential by this guy is minus Q 4 pi epsilon naught R2, right? And then, so Q 4 pi epsilon naught R1, R2. And then you can write R1 as a function of known variables. So what we know is R, D, theta, right? So how can we write R1 as a function of R and D and theta? You can use cosine law. So R squared plus D over 2 squared plus, is it minus? I'm always confused about this. Like, I guess it's plus 2, is it minus? 2R D divided by 2 cosine theta, right? And then R2 can be written like same thing, R squared D divided by 2 squared. And then in this case, this is the 180 minus theta. So it's like plus 2R D divided by 2 cosine theta, right? And then you can take R out, okay? If you take R out, then this becomes R1 plus R squared D squared 4 minus D divided by R cosine theta. And then similarly, this becomes plus, right? And then what we need to do is to do a Taylor expansion, right? Because we know that R is much, much larger than D. So D divided by R is much, much smaller than 1. So we can just ignore the second order and only keep the first order. So just we ignore this, okay? And then we have only the first order. And then if you probably know that 1 plus X can be Taylor, if you do the Taylor expansion, 1 plus X becomes 1 plus X divided by 2, right? Am I, are you guys following? Like, everyone knows about the Taylor expansion? Please raise your hand if you know about the Taylor expansion. Okay, so, okay, good. Thank you. So I just worried about you guys are not knowing about the Taylor expansion. Okay, so you know the Taylor expansion. So if you do the Taylor expansion and then keep the first order term, becomes like this, right? So if you do that thing for this equation, then this is R, and then 1 minus D 2R cosine theta, right? And then if you do the same thing for this R2, you have a different sign, right? And then now you go back to it's a 1 over R. Okay, so you need to do the Taylor expansion in a different manner. So you have to do the Taylor expansion for this thing, right? And then if you do the Taylor expansion for that thing, I guess it becomes a minus here. But anyway, it's an easy Taylor expansion. So if you do the expansion, you realize that the lowest order term, the 0th order term here, has the same sign for both R1 and R2. So if you take minus, this term goes away. The lowest order term goes away. And the first order term has different sign. So if you take a minus sign, it actually adds up, right? So the lowest order, the first order term survives. And if you do this calculation, and you get this. So again, V is Q divided by 4 pi epsilon naught, 1 over R1 minus 1 over R2, right? And then, so I calculated here in this manner, but it's not necessary to do it this way. It doesn't. You can also do it like expand it into Taylor series for both of these, and then combine it. And for both cases, the answer is the same. So you got V is Q divided by 4 pi epsilon naught d cosine theta divided by R squared. Okay. And then we define QD, Q multiply D as P, is which is called a dipole moment. And then you have a vector dipole moment, which has a direction like from minus charge to positive charge. So this is the dipole moment, the direction of the dipole moment. So QD AG is the vector dipole moment. And then if you take a dot product of AR, you get the cosine theta, right? So V can be written like this. So P dot AR 4 pi epsilon naught R squared, or P cosine theta 4 pi epsilon naught R squared. Okay. And to calculate electric field, you can take just a gradient of it, negative gradient of it, and you get this equation. And if you draw it, so this is your dipole moment, and then your electric field looks like this. It's like circling around your dipole. So so this is just one example of why the electric potential is useful in solving electrostatic problems. And as I said, you can solve the same problem just directly solving the electric field. No problem doing that, okay? But it's more complicated. You need to deal with each component of the electric field in a proper manner, and it's more likely that you make a mistake during you solve the problem. And instead, you can solve this in potential, and then taking a gradient of a potential, you get the correct answer. I think it's more reasonable way to solve electrostatic problem in most cases. So in most cases, people actually solve potential instead of electric field for electrostatic problem. Okay, so any question regarding this problem? Okay. If there's no question about this problem, I'll move on to the next exercise. By the way, do you hear the sound, the noise from outside? Can you hear the no? Okay. Okay, that's nice. That's nice. Yeah, seems like there's some cleaning going on outside, and it's pretty noisy in this room. But it seems like noise canceling works very nice, and you are only hearing my voice, which is nice. Okay, so now we can expand this concept of electric potential to charge distributions, as we did for Coulomb's law. So instead of a point charge, we can have line charge, surface charge, and volume charge. And you can expand it in this manner. It's no problem doing this, right? Line line density, surface density, volume density of the charges, and then you can do line integral, surface integral, volume integral. That's it. So if you have a distribution, you can do this. So here is one exercise. If you, I think it's probably good to try to solve this exercise. You have a disk, charged disk, with a fixed radius b, and then you want to solve electric potential at, or electric potential and field at this point, 0, 0, z. So I'll give you 3 minutes. Try to solve this problem using electric potentials. Okay, time is up. How many of you got the answer? Raise your hand. If you got the answer, raise your hand. Only a few. Okay. Less than 10%, less than 20%. Can you tell me why you couldn't get the answer? Was it because you don't know how to approach to this problem, or just time was too short? Like 1 and 2, like the answer 1, too difficult. Answer 2, too short time. Can you type in why you couldn't get the answer? Okay, Ichungpil said it's 2. Okay, good. Thank you. That's very nice. I was worrying that if this was too difficult, then it's kind of, there was some problem in my teaching. So thank you. So I mean, if you feel it's difficult, it's fine. But if the majority feels this is difficult, then probably we need to go back to the previous stuff and then start over. Okay, so how to deal with this problem? It's same thing. We the rho s, the density is a constant number, so it's just rho s. You can just take it out or whatever. And then ds prime, again, the primed coordinate is used for source position, and this is like a rho d phi d rho, right? That's the source position, and the distance between the point of interest to the source position is g squared plus rho prime squared, and take a square root, right? And then once you do that, because you can integrate over phi without any problem, so you can get 2 pi, right? And then you can perform the integration along rho prime, and then if you do that integration, you get this answer. Okay, so this is your V, the electric potential, and your electric field can be obtained by taking the gradient, negative gradient of your potential. This. Okay, and here I use some tricks like you. I just because I know that electric field only have the z component due to the symmetry, so I didn't even calculate other components. But so it's easy to evaluate this. But anyway, that's how you get the solution. And yeah, so that's, and again, you can solve the same problem by applying Coulomb's law, right? And then you can obtain the electric field due to this line, this small surface segment, and then integrate them all in a vectorial manner, and then obtain the electric field. That is perfectly valid way of calculating things, but it's just more complex. Okay. And here's a question. Now, like assuming that you don't know the answer, you don't know this answer. Okay, it's going back to this position. And then when z is much larger than b, then what would be your solution? Like when z much larger than b, then what's your solution for b? So when z is much larger than b, this disk looks like what? This disk would look like a point charge, right? It's a point charge. So exactly. So this is a point charge. Then we can apply the equation for the point charge, like a Q divided by 4 pi epsilon naught Z, right? Distance between the point charge to the, this is Z. And then Q here, of course, is pi rho, pi B squared multiplied by rho S, right? This is the total charge amount of this guy divided by 4 pi epsilon 0 Z, right? So we know this limit. And what about the other case? B much larger than G. What can we do? What's the situation? So what does it look like in that case? What is this? Right. As many people get the correct answer. Now this disk looks like an infinitely large sheet, right? And then we know the solution in this case, right? Electric field is what? Rho divided by 2 epsilon naught, right? So we know the electric field solution in this case. So even though we don't know the correct answer in like extreme cases, we know how this solution should behave. And then now assume that we get the solution, and then we test whether our guess was correct. So two limiting behaviors. The first one, B is much larger than Z, then infinite sheet of charge. Then if electric field is equal to this, right? Rho divided by 2 epsilon. And then when Z is much larger than B, then it becomes a point charge. Oh, yes, Fakhri, as Fakhri mentioned, this technique is same as Coulomb's law, right? Exactly. This is just solving the same problem in a slightly different manner. So instead of obtaining E field directly from the Coulomb's law, we obtain V first, and then take a gradient of it in order to get E. So it's in principle they are the same. It's just a mathematical or some some trick. Then you can solve the problem easier. So what I want to convey here is that it's easier to deal with potential rather than the field itself. That's what I wanted to say. Yeah, nothing is different in principle, and you get the same solution both ways. But anyway, if you do these, if you check the limiting behavior here, you can see this solution behaves exactly as you expected, right? Which confirms your solution, reconfirms your solution. And I want to recommend you to have this kind of habit. Like when you see the solution, try to, when you see a problem, try to guess the limiting behaviors. Like, what if Z is much larger than B? What if B much larger than Z? And then if you get the solution from complicated calculation like this, always test whether your solution pass your previous guess, right? If it doesn't pass, then it's highly likely that your solution is wrong, right? And then it's a good practice that you always guess the extreme behavior, and then test your solution, see if that satisfies this extreme behavior. Okay, so now in the next lecture, I will explain about the electrostatic energy. So far we've talked about electrostatic potential, and I'll talk about electrostatic energy next time, and then move on to electric fields in matters. Okay, so so now we will learn like how the how the material reacts to the applied electric field. Okay, so this is all I want to say today. Is there any question up to this point? Okay, if there's nothing, I'll stop here.